So our next talker is Vandit from Australian National University. So take it away.
All right. Thanks, Ken. Thanks for the invitation. And good morning, good evening, everyone, wherever you are. So today I want to talk mainly about this isomorphism between these three automorphism groups, and I'll introduce the groups and their automorphism groups in a second. And then very briefly, towards the end, discuss some implications, particularly for Aut F2, because automorphisms of free groups are quite widely studied. Also, I should mention, so this is actually a known result. It's been known for quite a while, but it's one of those that's until recently was not very widely documented. I think it has appeared in a couple of papers in the last few years. So I just wanted to make a few things explicit today. So the plan is to obviously introduce these three groups and their automorphism groups, and then I'll go through a couple of the proof sketches. And one of the things I've done recently is actually write down explicit isomorphisms between these groups that go both ways. And then, as I mentioned at the end, we'll discuss some implications for all three groups, but particularly for Aut F2. So let's start by considering these three groups. B4 is the braid group on 4 strands, which has this standard presentation. So we have the two braid relations and strands that are more than distance, or rather generators that are more than distance 1 apart commute. F2 is the free group of rank 2, and W3 is what we call the universal Coxeter group of rank 3. So it's the Coxeter group where the generators are obviously involutions, but those are the only relations we have. So every Coxeter group is a quotient of some universal Coxeter group. And what we're interested in is the automorphism groups of these groups. So let's look at presentations for each of them. Aut B4 is the semi-direct product of the inner automorphism group of B4 and Z2. So in B4 has index 2 in Aut B4, which is why we have this semi-direct product. And so this is a presentation for Aut B4. And just to explain what the generators are in this case, A, B, and C are what we started with before, but they're now the corresponding inner automorphisms by A, by B, and by C. And Z2 inverts the generators in this group. So you can think of T as representing the map that inverts A, inverts B, and inverts C. Aut F2 has, so this is a presentation that I've taken from Magnus, Karras, and Solitar from the first text from 1966. And again, let's look at what these generators are. P is a permutation or transposition. Since we've got two generators, it's the transposition that swaps X and Y. Omega inverts one of the generators, let's say X, and fixes the other. And U is a transvection that sends, say, X to XY, and Y it leaves that invariant. So obviously P and Omega have order 2, and then we get a bunch of other relations on the second line there. So at first, this presentation might not seem very intuitive, which is what we'll see with that isomorphism, looking at an alternative presentation for Aut F2. And finally, Aut W3 can be thought of as the symmetric automorphisms of W3 semi-direct product S3. So obviously we can permute the generators, and so that's where we get the S3 from. And then the symmetric automorphisms are those generated by the partial conjugations, where one generator of W3 conjugates another. And so that's where we get this presentation from. So the chi-ij's are the maps that conjugate Sj by Si. So Si conjugates Sj. And sigma 1 and sigma 2 are just generators of the symmetric group. And the action is what you would think it would be. The permutations permute the indices in the chi-ij. So that's where we get the semi-direct relations from. And as was in the title of the talk, the remarkable result is that these groups are isomorphic. So these three classes of groups intersect in some sense at these respective ranks. So let's look at sort of the proof sketch. And the idea of both proofs is the same. By both, I mean, we'll prove that Aut B4 is isomorphic to Aut F2 and Aut W3 is isomorphic to Aut F2. And the idea in both proofs is the same. What we're going to do is identify a characteristic copy of F2 in B4 and a characteristic copy of F2 in W3. And what I mean by characteristic is that the subgroup of that's isomorphic to F2 is preserved by every automorphism of the larger group. So for the first one, Aut B4 isomorphic to Aut F2, here's a subgroup that's isomorphic to F2, and you can see this in various ways. Perhaps the ping pong lemma might be one way to see that, and is characteristic in B4. And the map from Aut B4 to Aut F2 is naturally this restriction map. So because the subgroup S is characteristic in B4, any automorphism of B4 I can just restrict to an automorphism of S, and that defines this natural homomorphism rho from Aut B4 to Aut F2. So that map is a homomorphism. If I just restrict that automorphism of B4 to one of S, and S, as we said, is isomorphic to F2, and it's an isomorphism because you can verify that we have a generating set, that the images contain a generating set of Aut F2. And it takes a bit of work to see that the map is injective, which is why what I will show in a second is kind of useful of constructing an inverse. But the key is that the centralizer of this subgroup is trivial in B4, and so we get this isomorphism. The other isomorphism is exactly the same. So we have a characteristic copy of F2 in W3, and that's generated by, or rather is, in fact, the subgroup of even length words in W3, generated by, say, S1, S3, and S2, S3. And again, this subgroup is characteristic in W3. So you can probably guess that we have a similar map where we just restrict an automorphism of W3 to 1 on the even length elements, and that becomes, again, a homomorphism. That restriction map is a homomorphism, and it's injective and surjective as well. So exactly the same idea for this other proof. But as I said, it can take a bit of work to see that this map is injective, which is why one of the things I did recently was to construct explicit maps both ways. So naturally, the forward direction, we've got what this map is. So I can write down the images of the generators under the map rho and under the map pi. So for Aut B4 to Aut F2, a bit of work gives this. Ideally, I would do this in GAP, but this is something that I verified by hand. And we can construct an inverse to this homomorphism, and that's what we would get for the inverse. So you can verify that the relations hold and that they are actually inverses. And exactly the same thing. Oh, and I should mention, so these images are obviously they're automorphisms of F2 or of B4, but treat them as words. So they're compositions, but compose them from left to right rather than the usual right to left. And similarly, we can do the same thing for the other isomorphism. So obviously we have 8 generators for Aut W3, and you can map them over and do exactly the same thing. Now, constructing the inverse in this case is a bit easier because omega and p actually appear as images of generators of Aut W3. So the only one you need to think a bit about is the transvection, and that's not too hard either. All right. So what kind of implications does this have for Aut F2? Well, first thing is we had a presentation for Aut F2, which was perhaps not very intuitive, at least in terms of the relations. So we can now decompose Aut F2 in the way that we decompose Aut W3, which is as this semidirect product. And the symmetric automorphisms of W3 themselves can be decomposed as a semidirect product of the inner automorphism with W3. And so we get this alternative presentation for the automorphism group of F2. And of course, Aut F2 is linear, which means that going the other way, we get that Aut B4 and Aut W3 are also linear. And the next thing I want to talk about is this nice action of Aut B4 on a space called Bradys Space. So we'll describe what this space is now. So think about this enlarged generating set for B4. So the usual generating set would just have the A, B, and C. But if we introduce these generators D, E, and F and just call the word BACX, this is something that Tom Brady did, I think in the early 2000s. And so if we take this generating set, and I also consider length 2 subwords of this word capital W, we can construct a Cayley graph of B4 with respect to that set. But what we're going to do is we're going to change the edge lengths so that these vertices line up in a nice way. And I have a picture on the next slide. So what we're going to do is that A, B, C, D, E, and F, any edge labeled by those will have length 1. Any edge labeled by a length 2 subword of W, so something like BC or CA, AD, DE, and so on, would have length root 2. And X will have length square root 3. And why we do this, or why Tom Brady did this rather, will become apparent in the next slide. So if we construct that Cayley graph, things line up in a very nice way. So if I take, for example, this bottom left vertex in what we're calling Y0 to be the identity, then the edges B, A, C, or any of the single letter, so A, B, C, D, E, or F, will take us between these dashed lines. So it'll take us to a different dashed line. AC will take us again between 2 dashed lines, but it'll form the diagonal of this triangle. For example, B is this edge down here, and then AC is this diagonal edge. And then if you go vertically, that's an X. So the key idea in defining these edge lengths this way is to make sure that these vertices align so that along those dashed lines, you have essentially cosets of the subgroup generated by X. So you'll have the identity and X and X squared and so on, and you can go down. So you have these sort of cosets of X there. And if I project that space down, so you can see that there are 2 tetrahedra here, but this space can, I could have drawn a bit more of it, but you can go, to the left and right and into and out of the page as well. We'll get lots of these tetrahedra, and if I project that down, what we will get here is this space called Bradys Space, which we've denoted X0. And that turns out to be a systolic simplicial complex if I fill in those, if I fill in the interior of those triangles. And the great result is that Aut B4 acts properly discontinuously and co-compactly on that projection. And as a result of that, Aut B4 is cat0 and it is biautomatic. And so Aut F2 inherits those properties as well. And obviously Aut W3 too. And finally, a little bit on sort of other free groups. This thing that we had with the even length words in a universal Coxeter group actually holds true for higher rank Coxeter groups as well. So the subgroup of even length words in a Coxeter group of any rank, a universal Coxeter group of any rank, is isomorphic to Fn-1 and is characteristic in Wn. So that's always true. And so this map rho n we can define again to be that restriction is always a homomorphism, but the key is that it's surjective only for n at most 3 and it's injective for n at least 3. And so we get this isomorphism only in that case, Aut W3 and Aut F2. So that's why I think this result is kind of remarkable, even though it is a known result. But hopefully you haven't seen that before, or even if you have, you haven't seen the proofs, which is why I wanted to spend some time detailing those. And that is it, I think. Any questions?
What was the reference for that you showed? Is it Adam Piggott, Kim Rowan, Genevieve Walsh?
Reference for is
this one.
That's right. Geometric action is indeed, yes, this last one. Piggott, Rowan, Walsh. And
do you have reference to the Brady paper or not here?
I don't have one on hand right now. I know it's definitely referred to in this first Crisp and Paoluzzi paper, which is where they had this picture of this space. So it's definitely
Okay.
referred to in there. But that's the Crisp Paoluzzi one is what I used for that.
Okay, thanks. I'll look there. Yeah.
I think Brady and McCammond also did a lot with those shapes after Brady. Yeah.
Okay, thank you.
Vandit, my question, so what will you do from here? Like, it's cool to give an exposition of this because it's really good to know about. But where to from here?
Yeah, one of the things I'm doing now is getting this bioautomatic structure on Aut F2, or well, on any of the groups, and just translating it using those isomorphisms. So that's the first little project I'm working on right now. Going beyond that, I think one of the things that's of interest is to consider, for me certainly, working with Adam, to look at Aut Wn for n greater than 3, and see if we can sort of get these kinds of results for those groups. So the first thing would be to look at, we know how Aut B4 acts on that space. If I can just translate that and look at the fixed points with respect to Aut W3 and consider spaces which Aut Wn might act on, that would be sort of a natural step after this.
Cool.
Well, if nobody has any more questions, let's thank Vandit again for a nice talk.